The topic for this lesson is full-wave rectifiers. In contrast to the half-wave rectifier, a full-wave rectifier establishes a unidirectional current for the entire waveform or full cycle. The output voltage is a pulsating DC wave that has a frequency twice that of the input. The average value of the full-wave rectified voltage is determined by the equation 2 times V sub max divided by pi, or 0.636 times V sub max. Let's find the average value of the full-wave rectified voltage in the figure shown. V sub average is equal to 0.636 times V sub max, or 12.72 volts. A full-wave rectification circuit is now shown. A more efficient way of designing an AC to DC converter can be constructed using two diodes and a center tap transformer. If the center tap is grounded, the voltage as seen by the two diodes is always 180 degrees out of phase. Diode D1 is forward biased during one half of each input cycle, and diode D2 is reverse biased. During the other half of the cycle, D1 is reverse biased and D2 is forward biased. One and only one of the diodes is conducting at any time. Both half cycles are converted to DC pulses of the same polarity. The equation for determining the maximum voltage across the load is V sub max of the secondary divided by 2 minus 0.7. Or, if we neglect the drop across the diode, V sub max out is equal to V sub max of the secondary divided by 2. The maximum reverse or peak inverse voltage that each diode must withstand is the transformer's peak secondary voltage, or V sub max secondary. Applying Kirchoff's voltage laws, the peak inverse voltage is equal to V sub max of the secondary minus 0.7 volts. Since V sub max out is equal to V sub max of the secondary divided by 2 minus 0.7, or V sub max of the secondary is equal to 2 times V sub max out plus 1.4, substituting peak inverse voltage is equal to 2 times V sub max out plus 0.7 volts. Let's look at another example. Sketch the voltage waveforms across each half of the secondary winding and across R sub L when a 150 volt peak sine wave is applied to the primary winding in the circuit shown. Also, calculate the peak inverse voltage rating of the diodes. The total peak secondary voltage is determined by the equation V sub max of the secondary is equal to N sub S divided by N sub P times V sub max of the primary, or 1/2 times 150, which is equal to 75 volts. There is a 150 volt peak across each half of the secondary. The output load is 150 divided by 2 minus 0.7 drop across the diode. We know from the following equation that the voltage across the load is equal to V sub max of the secondary divided by 2 minus 0.7. Therefore, V sub max out is equal to 75 divided by 2 minus 0.7, or 36.8 volts. Each diode must have a minimum rating of 50 volt, neglecting the drop. The waveforms are shown in the diagram. Another type of rectification circuit is the bridge rectifier, which is now shown. A bridge rectifier combines the principal advantages of both full-wave rectifiers and half-wave rectifiers. Similar to the full-wave rectifier, the bridge rectifier uses the entire input cycle and is relatively easy to filter from pulsating DC to approximately true DC. The bridge rectifier does not require an expensive center tap transformer, and any AC voltage source can be used to drive it. A bridge rectifier is composed of 4 diodes arranged to form a square. 2 and only 2 of these diodes are conducting at any instant. During positive half cycles, diodes D2 and D3 are forward biased, while D1 and D4 are reverse biased. However, during negative half cycles, D2 and D3 are reverse biased, while D1 and D4 are forward biased. Neglecting the diode drops, the secondary voltage appears across the load resistor R when D2 and D3 are forward biased, as well as when D1 and D4 are forward biased. If the diode drops are taken into account, the voltage out is equal to the voltage of the secondary minus 1.4 volts. Assuming that D2 and D3 are forward biased, D1 and D4 have a peak inverse voltage equal to the peak secondary voltage. This is, then, also equal to the output voltage. If the diode drops are included, the peak inverse voltage across each reverse biased diode V sub max out is equal to V sub max out plus 0.7 volts. It should be noted that the peak inverse voltage ratings of the bridge diodes is less than that required for the center tap design. Bridge rectifiers are very useful, and they can generally be available as single monolithic components. A typical commercial bridge rectifier is illustrated in the figure. Determine the output voltage V sub max out in the figure shown. What peak inverse voltage rating is required for the silicon diodes? The transformers have a specification of 15 volts RMS secondary voltage for the standard 120 volts across the primary. The peak output voltage is, taking into consideration the two diode drops, V max of the secondary is equal to square root of 2 times V sub RMS, or 1.414 times 15 volts, which is approximately 21.2 volts. Therefore, V sub max out is equal to V sub max of the secondary minus 1.14 volts, or 19.8 volts. The peak inverse voltage for each diode is determined by the equation V sub max out plus 0.7 volts, or 20.5 volts.